Okay, welcome back to numerical analysis. So today I'm really just going to be talking about the homework and how to get through the homework. And here I pulled up some Matlab code. This is going to be necessary for the homework assignment, but when it comes to actually doing something on the exam, I'd expect you to be able to do it by hand. So I'm not going to expect you to take like 20 derivatives and find the maximum of that. I might expect you to take 2 derivatives of a function and find the maximum. I go through the details. I've done it in a couple of PDFs I've sent you guys, and this is going to be yet more information on how to help you with the first homework. Hopefully the second homework will be a little bit more organized with my solutions, but I just do this when I can. So I spent like 15 minutes coding up this thing that takes the nth derivative and finds the maximum through the n plus first derivative zeros, and then compares it with endpoints and sees if the critical points are within -1 to 1, and then evaluates all of them and then compares those answers for the maximum and dividing by n factorial, which gives you then a bound on the error, not necessarily the exact error, but an upper bound on the error that you can trust. But before we do that, I went ahead and I wrote up some notes talking about the first couple problems and things to look out for. So in summary, before we jump in there, there were 4 different problems I gave you. There was natural log of 1 plus x. There was sine of 5x, there was e to the minus x squared, and then there was 1 over 1 plus 25x squared. The first one is never actually going to have any good error estimates, and that's because it's unbounded on the interval -1 to 1. It has the vertical asymptote at -1. So there's no hope in getting any arresting any sort of error bound, arresting any error on the Taylor polynomials there, because any polynomial is always going to return a finite value on that interval, and there's infinite values in there, so your bound is infinite. The next 2 should be manageable in one way or another, and the reason for that is that sine and e to the x are both what we call real entire functions, which means that their Taylor polynomials converge back to them over the entire. So the radius convergence is infinity, right? So yeah. As long as you stay in -1 to 1, you can get a concrete error bound with polynomials, and so you can go ahead and do some computations there. Now, as far as the last one, I actually don't know the answer to that. The issue there is that we have a geometric series that we use to expand Runge's function, which is 1 over 1 plus 25x squared. Now, 1 over 1 plus 25x squared doesn't actually, that series doesn't converge on the interval -1 to 1. It only converges on -1/5 to 1/5. And that's just because we need 25x squared to be less than 1, which means that absolute value of x has to be less than 1 over 5. So we don't have a convergence Taylor series, but that doesn't mean that we're necessarily out of luck. It could be that the series actually converges. Sorry, not series converges, but it could be that the Taylor polynomials still get pretty close. We just can't guarantee that they're going to get as close as we like off to infinity. But they might be better than, say, an error of, say, 1/10 on that interval, or it might be better than an error of 1 over 100, or they might not do better than, say, 1. So yeah. That's just something we're going to have to play with and see if the errors dip down fast enough before we start diverging. I don't really have a whole lot of hope for that one, but each of these gives you a certain description of the strengths and weaknesses of Taylor series. Yeah, let's go ahead and jump into it. So I'm going to go through a whole bunch of problems of homework 1. I'm not going to complete everything to the nth degree, but I'll tell you how you can go about it and get this done. So there are 4 functions that we're looking at here. F of x is equal to ln of 1 plus x. There is f of x, which is equal to sine of 5x. There's f of x, which is equal to e to the minus x squared, and f of x equals 1 over 1 plus 25x squared. All right, and each one of these sort of brings something else to the table. Let's see. So I asked you to find the Maclaurin series centered at 0 for each one of these, or the Taylor series centered at 0. Maclaurin series are always centered at 0. And this is really a calculus 2 thing, and however you write it down, I don't care. The real numerical analysis bit is going to be coming down to the analysis of the error that comes from these polynomials. So we can go ahead and find the series that correspond to each one of these, and then we truncate that to find the individual polynomials. For instance, ln of 1 plus x, we know is actually equal to, say, the integral from 0 to x of 1 over 1 plus t dt. Right? Just basic fundamental theorem of calculus. And that inside one can be expanded as a geometric series. So we're going to have, this becomes a sum n equals 0 to infinity, negative 1 to the t to the n, or negative 1 to the n and times t to the n, and we're integrating this 0 to x dx. And so then this gives us the series n equals 0 to infinity of negative 1 to the n times x to the n over x to the n plus 1 divided by n plus 1. Okay. Then we can go and do the second one. Again, we just know the Taylor series for sine, and might as well just go ahead and use that. So this is going to be the sum n equals 0 to infinity of 5 to the 2n plus 1 times x to the 2n plus 1. Sine has a negative 1 to the n in there too, and divided by 2n plus 1 factorial. 3, we have e to the minus x squared, and that just goes straight into the exponential function. So it's n equals 0 to infinity. You have negative 1 to the n times x to the 2n divided by n factorial. So I'm just plugging into x to the n over n factorial. I'm just plugging in negative x squared. And the last one is, again, another power series. Is another geometric series, sorry. So 1 plus 25 x squared. And so this ends up being the sum n equals 0 to infinity of negative 25 x squared to the n. And so you can write this as sum n equals 0 to infinity of negative 1 to the n, 5 to the 2n times x to the 2n. Okay, so out of each of these, there's some things we should really take note of. So the first one and the last one, the radius of convergence, well, let's just say for the first one. So the radius of convergence for the first one is just 1. Right, and in particular, ln of 1 minus 1, which is x being equal to negative 1, is minus infinity. Right, so so there's no hope of convergence in negative 1 to 1, and any Taylor polynomial will have infinite error at x equals negative 1. Now they might have good error like in some sort of compact domain of that region. So if we'd say only looking at, say, negative 3/4 to 3/4, then we can get uniform convergence there. Or where we get a uniform error bound there, but as far as the interval negative 1 to 1, which is where we talk about a lot of this stuff, where I asked you to do everything, it doesn't. And so this is something you need to keep an eye out. The Taylor series really only is good for local estimates. Sometimes it works out well, and it'll work out pretty well with sine and e to the minus x squared. But those are like what we call entire functions. And so so those do admit that sort of thing. But so I'll just say
2 and 3 work fine. Now, as far as 4 goes, the radius of convergence it basically comes down to showing that 25x squared is less than 1, which means that absolute value of x has to be less than or equal to 1/5. And so, so the series doesn't converge. On, say, -1 to 1, but the Taylor polynomials might help. What this means is that while the Taylor series doesn't converge there, that means that you can't assume that as you get higher and higher Taylor polynomials that they're going to get to be more and more refined of error bounds. But there you can get so the error isn't going to go to 0, but you might be able to still get decent error bounds for maybe the first few Taylor polynomials. But you shouldn't be able to expect it to dip underneath any particular number that you want. But you can try and see what you get. Now, if you've been following lectures, then you notice that this is Runge's function, and so it looks like Runge's function doesn't really admit very well to Taylor series approximations, nor does it respond well to interpolation at uniformly spaced points. But that's sort of previewing something that comes up later. Okay, so this is problem 1, and so for problem 2, this is something that we can take a look at. Let's see. Now I'm just babbling. Okay, so 2, we already said 1 is hopeless. So there's no real reason to bother. Now for 2, this is sine of 5x, and we're trying to, in general, what we're trying to do is we're trying to find a bound on the error committed by third order Taylor polynomials, right? And we know that the remainder formula are, basically the overall bound on the error is going to be the maximum of the absolute value of the fourth derivative over c times the radius of your domain. And so this is, generally we'd put x minus a, but we want to replace this with something bigger so it works for all x's. And so the radius of the domain is just 1 here. And then I'm going to divide by 4 factorial. All right, so that's what we're aiming for. So for sine, that's actually pretty easy. For instance, we know that if I take one derivative of sine, so remember we're just calling this f of x, then f prime of x should be equal to 5 times cosine of 5x, and then f double prime of x is equal to 25 sine of 5x, and then we pop down -1, and then we get triple prime of x is equal to minus 125 times sine times cosine of 5x, and then the fourth derivative is going to be 625 sine of 5x. All right, so the fourth derivative of sine should give you sine back, but then we just have these numbers accumulating out by the chain rule. So you can see that if I take a look at, say, the maximum value of this quantity, well, we know that absolute value of 625 times sine of 5x was the largest value it can take. Well, on the interval -1 to 1, sine of 5x is going to complete at least one period, and so then that means that this is less than or equal to 625 times 1, and so this is 625. Okay. Now, so then that means that the overall bound on the error it's pretty big, honestly. 625 divided by 24. which is 4 factorial. Right, and there's no way to simplify that. 625 is composed of only multiples of 5, and since 24 it only has 3 and 2s, you can't cancel anything out. Okay, now I think I've already given you a video showing the third one, and in my notes I have a little bit more showing you how to do this all by hand. It takes a little bit more work, and in a moment I'll try to show you some stuff in Matlab. But then, let's see, other things to talk about here. Yeah, so how do we get to problem 4? So not problem 4, but 4. Okay, so this was f of x is equal to 1 over 1 plus 25x squared. All right, so let's go ahead and take derivatives. This is where I start regretting even assigning this. So the first one is going to be 50 times x divided by 1 plus 25x squared, and then we pick up a minus sign. F double prime of x is the derivative of the top, which is minus 50 times the bottom, 1 plus 25x squared, minus the derivative of the bottom. Oh my god. Well, times the top minus the top, so plus 50x times the derivative of the bottom, which is going to be, what, 2 times 1 plus 25x squared times 50x. Okay. And all divided by 1 plus 25x squared, and this to the fourth. Okay. Let's see. I can pull out a 50. So let's see. Pull out just 50. Keep things simple. So pulled out a 50, and now what do we have? We have 1 plus 25x squared, which is going to give me, say, 1 plus 50x squared plus 625x to the fourth. And that was a minus sign in front of all of those. Oh man. And then plus 50x squared times 2 plus 50x squared. Yeah. And this divided by 1 plus 25. Oh, I'm stupid. Ha. Okay. We can simplify this a little bit better than that. So not only can I factor out a 50, but it looks like there's a 1 plus 25x in both numerators and denominators. So this becomes, take out minus 50, and then on the top you end up getting 1 plus 25x squared plus 50x, and keep them, yeah, I'm sorry, now it's minus 50x. Times 2, which makes it 100. So 100x. And now, yeah, and then this guy cancels with one of those guys downstairs, right? So on the bottom we get 1 plus 25x squared cubed. Okay, disaster averted there. And so then we get this. This is minus 50 times 1 minus 100x plus 25x squared, all divided by 1 plus 25x squared. And now I'm just wondering if I can simplify that top at all. Let's see. If I replace x with 5x, what do I get? So it's 1 minus 20 times 5x plus 5x 20 squared. Does that factor nicely? No, it doesn't. Shoot. Goodbye. And sorry for my cell phone here. Okay. So, and so then you can continue this operation and try to see what you get. This should have been cube on the bottom. Oops. Let's see. So x is equal to minus 50 times 1 minus, so the derivative of the top, which would give me 50x minus 100 on the top times the bottom, which is 1 plus 25x squared cubed. Yep. Minus, say 3 times 1 plus 25x squared times 50x times the top, 1 minus 100x plus 25x squared. All of this divided by 1 plus 25x squared to the 6th power. Okay, and that should have had a square here. Okay, so now I can factor out 2 of those guys, and so this becomes minus 50 times, say 50x minus 100, then we get 1 plus 25x squared minus 150x times 1 minus 100x plus 25x squared. And all of this divided by 1 plus 25x squared to the 4th. Right, so just quotient rule again, and then just doing a little bit of factoring. Yeah, you can keep this going, and you can do, say, one more derivative. But honestly, when it comes to the exam, I wouldn't ask you to do this much differentiation. It'd probably be like 1, maybe 2 derivatives, and then find the maximum of that. Because, I mean, on the exam, you only have so much time. In the homework problems, I expect you to have a lot of time to sort of explore these ideas. And if you need to, it'd be fine with me if you just use computer algebra system just to figure out what some of the answers are. Just make sure you can do this on sort of lower level. Like if I ask you to say a Taylor polynomial of order 2 or 1, I'd be able to take, you know, maybe 2 derivatives down so you can take the maximum of the second derivative of the first derivative of the second derivative. Sorry. Just say practice. Anyway, yeah, okay. So that's the sort of approach that you would take there. And MATLAB, I'll show you how to find the maximum of that too. Okay, so then the next ones come up, and this is really a problem for the computer algebra system. So I gave you a couple of breakdowns on how you can do number 3, which is telling you to find what is the order of the Taylor polynomial do we need to give an accuracy of 10 to the minus 5 for each of the functions above. And so over the negative 1 to 1 interval. Now I told you already that the first one just isn't going to work. The next 2 there should be some order. It might be a really big order, and so you need to use a computer to find those. And the next one is a 1 over 1 plus 25x squared. I don't know if you'll be able to find that order or not, but we can go ahead and see if we can, and if we can, hey, we'll throw a little party. But since the Taylor series doesn't converge, there is a big question mark whether or not you'll be able to find the accuracy. It doesn't mean that you can't find it with a good polynomial, but there is going to be some limit to how small you'll be able to make that error uniformly over the entire region. You can, as long as you stay between negative 5 and 5, you will eventually be able to find a good enough error bound there, but over the entire interval, negative 1 to 1, you won't be able to. And so these problems are really good because they allow you to explore different sort of limitations of the Taylor series, where the first one tells you that basically there's an infinite pole, and so you can't do anything about that. And the next 2, relatively fast convergence. I mean, it's reasonable to find something there, and then the fourth one is a big question mark because the series doesn't converge, but Taylor polynomials do exist because those are finite operations. And so, okay, so number 3, I'll sketch up a quick algorithm, and I'll give it to you guys if you want to play with it. And but then let's go ahead and talk about number 4. So number 4, I just want you to prove that the limit as x goes to 0 of 1 over x to the n times e to the minus 1 over x squared is equal to 0 for all n. 0, 1, 2, etc. And honestly, this isn't too bad. If we go ahead and take a look, basically what we want to do is we want to use the Hopital's rule. But Hopital's rule gets to be kind of hairy when we have an exponential function on the top, for instance. We can try. So let's see. So we have this guy as x goes to 0. We get negative infinity inside of e, so e to the minus infinity is 0. All right, and on the bottom we have something going to 0. So what we could try is this. We can say the limit as x goes to 0 of e to the minus 1 over x squared divided by x to the n. Well, that is going to be equal to the limit of the derivatives. So limit as x goes to 0, and we'd have minus 1 over, so the derivative at the top is going to be what? So the derivative of minus 1 over x squared is going to be minus, and we're going to have negative 2 over x cubed, I think, and this is going to be e to the minus 1 over x squared divided by n times x to the n minus 1. And so this ends up giving you some constant times the limit as x goes to 0 of e to the minus 1 over x squared, and then on the bottom we very inconveniently have increased the exponent by 2. So if we were trying to set up some sort of induction argument, this would just fall on its face, and the reason why is because the the reason why we're running into problems here is because this we have the minus 1 over x squared. Okay, so the next step to try is to try logarithms, and so that way we get rid of the e at least. So now I see that the ln of e to the minus 1 over x squared over x to the n is equal to negative 1 over x squared minus the natural log of x times n, right? Now if I go ahead and multiply top and bottom by x squared on the other one, find a common denominator, then what I get is negative 1 minus n times x squared times ln of x divided by x squared. Let me just double check that. Yep, okay. So everything's correct so far. And so ultimately I want to show that this is going to be going to 0. I want to show that this term is going to 0, and so that if this term goes to 0, then I'm looking for, we want basically this to be going negative infinity. But first we need to verify that we can even use Hopital's rule. Or is that even necessary at this point? So what do we have here? We have x squared ln of x. And so we can say, what is the limit of x squared times ln of x as x goes to 0? So that is actually going to be 0, right? And the reason why is because x times ln of x goes to 0, or x to any power times ln of x goes to 0. Again, this is Hopital's rule. And so that should be, you can demonstrate that, or maybe we'll demonstrate that in a second. And so then basically this term here goes to 0, this term goes to 0, and so basically this is tending to negative 1 over 0, and that's going to give us negative infinity, right? And so thus the limit as n goes to infinity, x goes to 0, of the ln of e to the minus 1 over x squared divided by x to the n is equal to minus infinity, which tells us that the limit as x goes to 0 of e to the minus 1 over x squared over x to the n is equal to 0. Now, keep in mind, since you are approaching a vertical asymptote, you have to be worried about whether or not you're going to an asymptote like this, where you just say the limit doesn't exist, or you're going to something like this. That's what you're looking for. This would say going to negative infinity, and the only difference that would happen here is if you had something flip signs on either side of this. But since this is going to -1, it stays solidly as negative, and since this is x squared as you go into 0, that's going to stay positive. So on either side here and here, you end up being going to negative infinity. So that's where that comes from. This you can show with the L'Hopital's rule again. And that really just comes down to, if we want to actually verify this with L'Hopital's rule, this becomes the limit as x goes to 0 of, say, ln of x divided by 1 over x squared. And let's see, so this is going to be the limit as x goes to 0, derivative top, 1 over x, over the derivative bottom, which is minus 2 over x cubed. Is equal to the limit as x goes to 0. So then you flip everything up, and so then you get basically what x squared times divided by -2, I think. And yep, and so then this goes to 0, right? Okay, so then that's number 4. So basically just some calculus 1 reasoning. I'm not asking you to do anything really complicated here. So basically this is a big review of Calc 1 and Calc 2 concepts. Now I'll jump in and show you some Matlab code to help you find the maximums of the other things. These you should be able, again, for number 3, you should be able to come up with for problems 2 and 3. You should be able to do this for like the first or second derivative on the exam. Keep that in mind. But it is important to know how to do this for higher orders, especially if you're being demanded to find some very particular accuracy, which does come up from time to time. Okay, so with that, I'll stop and we'll jump into the Matlab code. So those were the first couple of problems. Now I want to jump in and talk about some Matlab. I have the Matlab code I made up earlier. It took me about 15-20 minutes. It would take you a little bit longer, and I'll post this up on Canvas. So first, let me go ahead and get a screen recording going. Let's move that over here. And yeah, that should be good enough. Okay. Yeah, let's do it. Okay, so we're gonna record. Options, we have this Yeti mic, and cover that, and save to desktop. I've actually lost entire recordings before because some blip, so I'm just hoping everything's going to work out. Yeah, I'll be really frustrated if it doesn't. But at least I've already coded up everything. I didn't want to take up all that time, but I'll describe the code as we go, and yeah, and then you can fiddle with it. This is really just for you to go and press play and see what happens. All right, so let's go ahead and start recording and jump into it. Okay, so let's see what we have. So if we take a look here, that we're using the Symbolic Toolbox. Now, the Symbolic Toolbox allows us to define functions inside of Matlab that don't lose a variable. So we're not, converting anything to, say, floating point precision or double precision or anything else like that. Matlab will see this as, say, in this case, the exponential of negative x squared, and that's how it interprets it. And it sees these as sort of a symbolic variable that it can take derivatives of and do all these other things. And so that's our function. And then what we're going to do is we're going to run a loop. And so in each one of these loops, I'm taking another derivative, and I'm finding the maximum of that derivative. And then by doing so, we can get an upper bound on that term that is a maximum of x from -1 to 1 of the nth derivative of f. So to start off, we take f and we take its derivative, and we replace f with it. We don't need to have an accumulation of all these guys. Now I choose I going from 1 to 100, 1 corresponding to the first derivative, 100 corresponding to the 100th derivative. I just put 100 here because we just wanted to make sure it goes out, but we want it to stop eventually. And if we don't find it by 100, maybe we should just give up. We can make it to 1,000 or 10,000 or something like that, but it's going to take more and more time. But if we're not seeing anything good happening by 100, maybe we should just stop. So then in here we start off by taking the next derivative past f. This will allow us to find the critical points of f and then evaluate those in order to see if we can find the maximum and minimum. And so that's exactly what I do. If you use the solve on a symbolic function and you don't put anything else in there, then it'll look for that guy being equal to 0. And then it collects all those points into what we're calling the critical points variable. This is a symbolic variable, and so it'll leave in, say, square roots in there, and so, like, for instance, if it was like 1 plus square root of 5 over 2, that's exactly how it would record it. But that's not very good for comparisons, and it takes a little bit extra time to call it. So I'm going to go ahead and convert all these guys to double, which is basically I'm changing it to a decimal precision. So then after that, I am looking for the absolute value. Now this is a bit to unpack. First I'm saying to substitute in to this f, which is a derivative of f, of the original f we have. I said just plug in 1. And now I want you to convert that. Now it's going to be a symbolic answer, so I say convert that to a decimal. And then I want you to take the absolute value of that decimal. Okay. Now what's going on here is I'm trying to find the maximum value over -1 of f. And 2 places that you need to check outside of the critical values are going to be at -1 and 1, or at the endpoints of your interval. And so I take the maximum of these 2 points, -1 and 1, and I put them into this maximum value. Now this loop goes through each one of the critical values that we found, evaluates f there, and if that evaluation is bigger than if the absolute value of that evaluation is bigger than our previous maximum value, we replace the maximum value with that. And then we keep on going. And each of these maximum values we divide by the factorial of the number of derivatives that we've taken. So so here we divide it by the factorial of I, and factorial of I here as well. So here's it. This is what it says, that if the maximum value is less than whatever that value was at the critical point divided by the factorial, then I want you to replace that maximum value with the new value, this. Okay. So it goes through that, and it looks through all of these different points, and then whatever it does, you now have you have the maximum value on that interval. Now we set this threshold. We wanted it to be smaller than 10 to the minus 5, and so we check and see, is this bit less than 10 to the minus 5? And if it is, well, we'll tell you. So I have this display command, which just puts a little prompt. You can see I've already found for this particular function, this error bound at 10 to the minus 5. Now break tells you to leave the loop. There's 2 commands for loops that can be helpful. Continue means just to skip everything else in the loop and just start all over. And break says stop the loop here. Now this prevents us from continuing on and trying to find more values, and so that seems to be a good way to stop. And if you didn't find it, well, then replace f with its next derivative and do the whole thing again. And so then that we're going to see how many tailored polynomials we need to descend by taking more and more derivatives as we go, and then finding the maximum, the error of that next derivative. So then for this one, if I go ahead and press play, well, I guess I already found the answer, and so to save a little bit of time, it tells us that we need a Taylor polynomial of order n equals 16 in order to be sufficiently small. That'd be a lot of derivatives to take by hand of this particular function. And then we can go ahead and try different things. So that was for the exponential. I could try, say, sine of 5 times x and see what we get there. Give it a second. And so here we need even more. We need 20 derivatives. And here it's showing us that, this is the 20th derivative of sine of 5x, and so of course it's just a sinusoid, but it's 10 to the 14 up here. But remember, we're dividing by 20 factorial, so that's going to take that down really small. And so then 10 to the 14 divided by 20 factorial turns out to be less than 10 to the minus 5. So we do good there. Okay, so now let's see what else. Natural log of 1 plus x, hopeless. We're not even going to bother. But what about 1 divided by 1 plus 25 times x squared? Let's see if we get anywhere with that. My guess is no, and so it's probably just going to stop eventually. I didn't actually put a comment if it doesn't find anything, so I guess we just wait for 100 iterations. And yeah, so I hope you guys have been enjoying the class so far. I know that being sort of asynchronous leaves it hard for me to communicate with a lot of you guys. I try to send out messages to all of you guys, and thank you for all of you who responded. And yeah, I'm just trying to make things as easy as possible for everybody here. When I signed up for Teach This class, I thought I'd be doing it in person. But now I'm in a household full of screaming toddlers, and I have almost no time to record anything. And it puts me in a panic because I have to teach a graduate course on a subject I've never even studied before. I knew like about 40% of the graduate course I'm teaching, and now I have to fill in the other 60% while watching children and juggling everything. Because my wife works too, and so basically we have 2 full-time jobs that we're trying to manage while we're watching children. This is really, really hard, and I really appreciate you all sticking with me. Alright, so I see that this thing just keeps going. We haven't hit 100 yet, but that might take a long, long time. Let me just pause it for a second and see where we got. Let's continue. Let's see, I can pause it by, say, clicking this. Let's see where we get. Boop. Alright, we're at 43. The maximum value last time was 10 to 29. You see that here. Yeah, we might as well just stop, honestly. It's not going to get better. So Runge's function doesn't seem to admit a good convergent Taylor series on -1 to 1. We knew that the series didn't converge. We were hoping some of the Taylor polynomials might get small enough, but apparently not. So, but yeah. And I guess I think that's it for homework 1, and I don't think I can give you any better answers than I've already given you. Anyway, so I'll put this code up on Canvas, and you guys can go toy around with it, and something really similar will be helpful for interpolation as well. Okay, well, thank you for watching, and I hope this helped you understand sort of homework 1 for our numerical analysis class. All right. I'll see you next time.